So welcome everyone to today's session of Emerging Topics in Biomolecular Magnetic Resonance. My name is Arthur. On behalf of the other organizers, I'd like to welcome the audience, thank speakers in advance today for their presentations. The slide that you see now has important information for you. First is the website, where we're posting information about the series. The second piece of information you can see is we follow the Gordon Research Conference policy. Please do not record audio or video of the lectures during the lectures. With the speaker's consent, we are recording the lectures and then they'll be posted at the ICMRBS YouTube channel shortly after the lectures, and the YouTube channel is shown here. You don't have to write down the channel. It's available on the website for the sessions. So with that, I'd like to introduce the first speaker. Oh, I should also have said that the speakers will give their lecture without interruption, and then we'll have a question and answer session after each speaker. Enter your questions in the Q&A module of Zoom. Don't enter into the chat. I won't be monitoring the chat very carefully. I'll be monitoring the Q&A. I'll ask questions to the speaker on your behalf. If you would like to ask a question yourself or a follow-up, use the raise your hand function and we will unmute you. At the end of both sessions, we'll end the formal presentations, but we hope the speakers will be available informally for a little while after the formal session to answer any questions we didn't get answered. So with that, I'll introduce today's speaker. Haribabu Arthanari is going to talk to us about his recent work on repurposing fluorine-19 NMR for the modern age. He received a bachelor's degree in chemistry from Madras Christian College and master's in chemistry from the Indian Institute of Technology in Madras. He then moved from India to the US for PhD studies at Wesleyan University in Connecticut with Phil Bolton, earning his PhD in 2004. He then joined Gerhard Wagner's laboratory as a postdoc and then took an independent position as assistant professor at Harvard in 2016. His work is a mix of elegant development of NMR methods, both pulse sequence development and computational optimization of experiments using optimal control and other methods, with a focus on metabolomics, protein-protein interactions, and across a range of biological systems, including transcription factors. So with that, Hari, thank you, and we look forward to your presentation.
Thanks, Art. I'm just going to start sharing my screen. I hope everybody can see the screen and hear me. Once again, I'd like to thank Art for that kind introduction and the fact that he has to listen to the same talk as he was also a part of our advisory committee a few weeks ago. And I'd like to thank the organizing committee.
I'm a slow learner, however, Hari.
I'd like to thank the organizing committee for the opportunity, and I'd like to also thank all the audience. I think it was from different parts of the world who are in different time zones who have made the time to be over here. So today I'd be talking some of our recent work on using 19F NMR to look at biomolecules, and especially the possibilities of using 19F NMR to look at large biomolecular system, given the fact that the nuclei, the atom 19F, is not native to at least higher eukaryotes. The opportunity of introducing a 19F labeling into biomolecules actually dates back to 1961, where the researchers fed fluorophenylalanine, which is the same molecule that I'm going to be talking about today, into live animals, and these are rabbits. And they've shown here that the fluorophenylalanine gets incorporated into proteins, and the proteins were active, and they were active and stable, comparable to the proteins, to the endogenous proteins, which do not have the fluorinated version of the phenylalanine. So this labeling is pretty old. But the idea of using 19F-NMR to biomolecules, at least solution biomolecules, is also not something that's new. Some elegant work by Angela Groenboom, who have shown the use of PREs in combination with tryptophan labeling. And there's work by Scott Prosser, Brian Kobilka, and Kurt Wurthrick using 19F-NMR to look at GPCRs. And here they use the CF3 group. And there's also work by, again, Scott Prosser and Will Pomeranz in labeling aromatic amino acids, and especially Will develop this method called the protein-observed fluorine NMR. All these techniques that I showed over here, these studies use one-dimensional fluorine NMR, and here I'm going to tell you about what are some of the limitations of using fluorine NMR to large biomolecular system. For that, we need to look at what I call the pros and cons, or the good, bad, and ugly of using F19 NMR. Let's first start with the advantages. As you know, F19 is a highly available natural abundance at 100%. It has a gyromagnetic ratio that is pretty high, comparable to that of proton, which promises us higher sensitivity. It has strong dipolar couplings. You can use this in for both fluorine-fluorine as well as fluorine-proton nosy, and there's some elegant work done on the solid state side by Mei Hong and Tatiana that leverage this. They also have strong scalar coupling, but for me the most attractive property of fluorine is the sensitivity of the fluorine chemical shift to its local environment, and where the chemical shift ranges a span of about 600 ppm, and this could be used to create resolution, and it also could be used to investigate dynamics and interaction. The other property that's worth noting is that the fluorine is an isostere with hydrogen, so which means if you're replacing a fluorine with a hydrogen with a fluorine, you get pretty much the same size, though not the same electronegativity. Now, if you come to one of the bad parts of fluorine NMR, which is one of the properties that I said was an attractive property, which is its sensitivity to the local environment, its chemical shift spans about 600 ppm. So in this case, when you're on a practical side, when you're about to pulse these nuclei, you run into the problem of finding pulses that can excite the entire gamut of the chemical shift. So here is some work done by Paul, and as many of you know, fluorine NMR is also used in fragment-based screening. And you can see that here's a collection of 10 fragments of small molecules that harbor fluorine. And you can see the chemical shift is ranging over about 70 ppm. And if one wants to do some either 90 or even 180 to do some CP&G experiments, that's going to be a problem with this large chemical shift range. So what Paul was able to do is to carefully select the bands that harbor the resonances, and only excite or only invert those bands using optimal control pulses. And now we can cover anywhere from 55 to 100 kilohertz range with these CP&G pulses that are substantially lower in power, because we don't concentrate on those sections of the spectra that do not have lines. And this is a property that is applied to small molecules, and it could be also used with proteins, especially when you want to do dynamics with 19F. But here is the ugly part, which is the most important part that limits the use of fluorine NMR to large molecular weight systems. And that is the large chemical shift anisotropy of fluorine that contributes to very fast T2 relaxation. To give you an idea and put this into perspective as how bad this problem of CSA is, let's take a toy system, a model system. Here we have an aromatic ring with a fluorine attached in light blue, which is attached to a peptide bond. You can see the carbonyl, the NH, and that's attached to a metal group. And now if we were to calculate the CSA tensor, and this was done using spinach, this looks roughly like this. So now you can see that big pink entity that looks like a Death Star, that is the CSA of fluorine. And you can look, compared to this, you can look at the CSA of the aromatics over here, the CSA of carbonyl, and also the CSA of methyl. Even though methyl looks bigger, the CSA of methyl is rather symmetric compared to the CSA of fluorine. Now, to give you another flavor of the effect of this particular CSA, here we plot the transverse relaxation rate as a function of magnetic field for MBP, which is about a 42 kilodalton protein with a tau C of about 25 nanoseconds. And here are the things that we solution state NMR spectroscopists often complain about is the CSA of the aromatic and the CSA of the carbonyl, which has this quadratic behavior increasing with the field strength. Now, when I add the CSA of the fluorine, those looks pretty insignificant. The carbonyl and the aromatic look pretty insignificant. So it is this, the effect of this CSA that has limited the use of fluorine to very large molecular weight systems. And this was in a conversation at one of the Euromar in Denmark, where Ko and I talked about leveraging a trick, an old trick from the book. Can we use the TROSY technique, and in this case, the version of TROSY that was applied to aromatic residues by perversion, we were initially thinking to offset some of the relaxation of either the fluorine or the carbon that is attached to the fluorine in the case of an aromatic system. Earlier, we had published some work on expanding on the aromatic proton-carbon TROSY by perversion, by using pyruvate labeling so that you can negate the one bond CC coupling that's about 60 hertz. So in order to do this, we need an aromatically labeled amino acid that is C13 labeled as well as fluorinated. So for this, we took a page out of the playbook of Scott Prosser, who has done this earlier, and with the help of Vlado Gelev and Danny Raveda at the Sofia University, we were able to produce this tyrosine that's fluorinated at the 3 position. So the way it's done is that you can see the 3 C13 labeled tyrosine can be commercially purchased. And now using this reagent called Select Fluor, which is a fluorine donor, in a single step, leveraging the acidity of these 2 hydrogens, you can actually substitute one of the hydrogens by fluorine. By carefully controlling the stoichiometry and the time, you can steer this reaction to a singly fluorinated form. The one thing which I want you guys to notice in this particular amino acid is that we have 2 carbons that are C13 labeled. One of them is attached to a fluorine and the other is attached to a proton. So if you make a protein using this particular amino acid, you can record the carbon-fluorine correlation as well as the traditional carbon-proton TROSY. And this, we're going to use it for comparison of the 2 different TROSYs. Okay, so now we have an amino acid that is C13 labeled and fluorinated. How are we going to incorporate this into a protein? The way we do it is using this reagent called glyphosate. So we grow the protein in minimal media as usual. And just before induction, we add this, the chemical glyphosate, which is the one that probably you guys have seen in news, it's in Roundup. And what glyphosate does is that it inhibits or it stops the production of amino acid by inhibiting a key step in the shikimate pathway. So now the system is no longer able to produce aromatic amino acids, and now we have to supply the aromatic amino acids. Now, if we supply the 3-fluorotyrosine along with unlabeled tryptophan and phenylalanine, the system will incorporate the 3-fluorotyrosine into the system. Others have shown that you do not need to add glyphosate. If you just add these amino acids, they automatically get incorporated, but the level of incorporation still needs to be investigated. So now using this, we're able to incorporate carbon-13 fluorinated tyrosine into our system. And Andras went to measure the TROSY, and we took our favorite sample, GB1. And GB1 has 3 tyrosines. And here I show you the carbon spectra of C13 labeled tyrosine. And these are the carbon that is attached to the fluorine. And you can see a pair of doublets here. The doublet comes from the carbon-fluorine scalar coupling, which is about 240 hertz. And you can immediately see the TROSY effect screaming at you at this 1D spectra. You can see the pair of doublets here. One of them is extremely sharp, and the other one is broader. And there is your cross-correlation between the dipole and the CSA. So now using the help of Ilya Kriprov and spinach, we are able to calculate what would be the Trosi effect, or what would be the relaxation of the Trosi component compared to the decoupled component. And here I show you on the top left part, the Trosi in red and the decoupled component in blue. You can see about an 18-fold, a factor of 18 slower relaxation rate for the Trosi. And you can see the Trosi relaxation of the carbon that is attached to a fluorine is actually slower than compared to the carbon that is attached to a proton. And similar to what was observed previously with the proton-carbon Trosi, the Trosi effect is only enjoyed on the carbon side, but not so much on the fluorine side. And this is something that we wanted it to happen, and that didn't happen. So we thought we'll see the Trosi effect both on the fluorine side as well as the carbon side. But I think the CSA of fluorine is way too big to get any benefit from the dipole. So the Trosi effect here is felt by the carbon that is attached to the fluorine. Now here is a comparison, because I told you that the same sample could be used to record both the CF as well as the CH Trosi. And here's a comparison that quickly shows you how better or how the CF Trosi is. What you see on the left-hand side is the CF Trosi. And you see a little splitting over here, a doublet that comes from this carbon-carbon 3-bond coupling. On the right-hand side, you see the CH Trosi, which is this carbon. And you can see the lines are broader compared to those carbon that's attached to the fluorine. And the other thing to note here also is that the Trosi component is the opposite one. It's actually upfield shifted in the case of CF and downfield shifted in the case of CH. And that's because of the coupling between carbon and fluorine is a negative 240 hertz, as opposed to a positive 160 hertz in the case of CH. So now, we went ahead and calculated what would the Trosi effect be for other substitutions, not only 3-fluorotyrosine, but other substitution on the aromatic ring. And we can show that for about 10 different substitutions, all of them enjoy the same Trosi effect, some more than the other, where we can see extremely slow relaxation rates for the carbon that's attached to the fluorine. For example, some of them it almost goes to a single digit, less than 5 hertz. And this is again calculated for a protein that's 42 kilodaltons, it's MBP. So now comes the question is that how do we record this Trosi component in a spectrometer? So naively, what we thought was we'll use a standard ST2PT pulse sequence in an out and back fashion. So we start with the 19F magnetization, we transfer it to carbon, and we encode the carbon and then use an ST2PT to select for the Trosi component, getting back to fluorine and record it on the fluorine. The reason is that traditional knowledge tells us that if we start with the high gamma nuclei, that's fluorine, and end with the high gamma nuclei, you get better sensitivity. So here is a spectra, here's a decoupled spectra on your left, and here is the coupled spectra where we just did not decouple. You can see the 4 components, 1, 2, 3, 4, and you can see the Trosi on the carbon being very intense, and for some of the resonances, we don't even see the anti-Trosi on the carbon. And here's the Trosi selection onto your right-hand side, shown in green, and we see that we are picking up the right component, which is the top right. And we do that by just changing the phases of the pulses over here in the ST2PT. But we were a little bit disappointed that we did not see all the resonances that we expected in MBP. Then we went back to the drawing board and we figured out that the reason is that whenever fluorine is transverse, it relaxes really fast. And here I show you the transverse relaxation for the different components that you would expect of magnetization that you would expect in the Trosi experiment. And you can see that any magnetization, doesn't matter if it's what it is, where fluorine is transferred, it relaxes really fast. And you can see that's mostly dominated by the CSA of fluorine. So we changed our strategy, and instead of going for an out and back, we thought we'll use an out and stay pulse sequence. So essentially limiting the number of the amount of time that fluorine is transversed. And we tried to do 2 different flavors of this. One is starting with the fluorine magnetization and then ending with the carbon magnetization, or the other way around, starting with the carbon magnetization, encoding it, and using an ST2PT, ending with the fluorine magnetization. And after some trials, we decided to stick with the part where we start with the fluorine magnetization and end in the carbon for two different reasons. One is that the resolution that you're going to get, the TROSY benefit is on the carbon. You might as well put it on the direct dimension so you can get the maximum resolution. The second is compared to carbon and fluorine, carbon has a slower T1 relaxation rate. So I rather start with the fluorine so that I can minimize my the recycling delay. So here are some comparisons. Here is the out and back TROSY, and here's the out and state TROSY, which is in this case, in the middle one, B is fluorine detect, and C is carbon detect. Now you can definitely see in the out and state, the shortened version, you see definitely more number of peaks. The resolution in the carbon is phenomenal. And in the below, I show you the 1D traces along the carbon and the fluorine dimension. And this is again a marker to say that why in larger systems, you definitely need the second dimension to disperse your signal because of the overlap. Now, here is a slide where I show the advantage of the CF TROSY when compared to the CH TROSY. Here again, the molecule of investigation is MVP. And as I told you, you can record both the TROSYs on the same sample because of the way the molecule is labeled. On the top, we show the CH TROSY at 25 degrees and the CF TROSY at 25 degrees. Both of them have resonances, and then the resonances are sharper in the CF TROSY. In order to make this a little bit more dramatic, we dropped the temperature to about 10 degrees to mimic a protein that's even larger. And now you can see that the CF TROSY has beautiful resonances, whereas the CH TROSY has only one of the very few fastly moving loops that are visible. We also applied this to the 180 kilodalton alpha 7 ring of the 20S proteasome, the system that was worked by Lewis K. And we were able to see pretty much all the expected peaks. So it's about 8 to 10 in this particular sample. Now, to summarize this part, what we found out was the CF TROSY is probably one of the slowest relaxing resonances that we know yet in a biological system. We compare the theoretical relaxation rates of CF TROSY compared to an NH TROSY, the appropriate magnetic field, as well as the aromatic effect of the CH TROSY in an aromatic system. Now, when we published this, there were some things that we were not quite happy about. One is that the choice of the system that we decided to go with. So essentially here, what you're doing is that we are substituting a hydrogen with the fluorine at the 3 position, which electrostatically could be a big deterrent to the structure of the protein that you're incorporating in. The second and most important factor is that the 3-fluorotyrosine is not symmetric. So now what's going to happen is that the rim flips are not going to be the same anymore. So people like Josh Wan who are studying these ring flips might see something that are different. So for example, if you consider this particular amino acid incorporated into the protein, now let's say the yellow part is a favorable interaction with the fluorine compared to the brown part, then what you will expect is that the ring flip is going to be more pushed towards the yellow part compared to the red part. That's one of the disadvantages. And the second disadvantage also is that that we were kind of not very happy about is that you see this beautiful TROSY effect along the C13 dimension, but still the F19 dimension relaxes really fast. Is there something that we could do about this? So with these 3 things in mind, we decided to go after 4-fluorophenylalanine as an amino acid that we'd like to incorporate. The advantages here is that by replacing the OH by an F or by replacing at this particular terminal position, what's going to happen is that it's going to be symmetric with respect to the ring flips, hopefully. And the other idea we had was, so instead of relying on encoding the fluorine frequency, which suffers from CSA, what if we correlate this hydrogen that is at the meta position to this carbon and leverage the TROSY effect that comes from this particular fluorine? So essentially what you're going to see is a 3-bond coupling from this hydrogen to this particular carbon, but we're also going to take the TROSY effect to make that carbon relax slower. So again, we went to Vlado and Danny on this, and that was pretty much the reaction they had when I asked for them for this particular amino acid, but yet they came through. So we can get the 4-fluorotyrosine commercially. And we decided to deuterate these 2 positions because that's pretty relatively easy to do because of the acidity of this. And the reason we want to deuterate it is that because we're going to correlate this hydrogen with that particular carbon, and we want to slow the relaxation of that particular hydrogen. And these two are the closest dipoles, and so essentially we decided to deuterate that. And then after a few protection steps, they will be able to use select fluor and convert that into a fluorine. So now this amino acid has a carbon label over here. It has fluorinated, and these two are deuterated, and the meta position is protonated. Now, in order to record the TROSY, correlating this carbon, this hydrogen with this particular carbon, Abhinav came up with the scheme where he uses an IPAP. So the pulse sequence works like this. So we first start with this proton magnetization. Then we transfer the magnetizations to this carbon using the long-range coupling. And since the transfer time is pretty long, we also encode the chemical shift during the process using a constant time encoding. Then all we need to do is refocus the magnetization once it's on carbon and then detect the magnetization. But during this refocusing time, we can also introduce a pulse on the fluorine to let the coupling between the carbon and fluorine evolve or not in an in-phase, anti-phase matter. And then we thought we could use this trick to select the TROSY component of the carbon with respect to the fluorine. So very simple, you go from proton to carbon, then you refocus it, and during the refocusing step, we do an IPAP. When we recorded the spectrum, and here we changed our system, the system we are studying right now is human carbonic anhydrase, which is again a 30 kilodalton protein. We got this beautiful spectrum and we couldn't see the antiphase peak. So essentially what you should see is that you should see another doublet, and we didn't see that. So we worked for a couple of days tweaking the pulse sequence to see what was wrong with the pulse sequence before we realized the fact that the anti-TROSY already has relaxed during the refocusing time period, and we need not do any IPAP selection. So in order to convince that this is exactly what is happening, we recorded a simple proton carbon HSQC, again transferring magnetization from this proton to this carbon. And what we did was, this is so essentially you go from proton to carbon using an INEP, you encode the carbon magnetization. What we did was we sandwiched a variable delay where everything is refocused at the end of the encoding time period. Now you can see that when that delay is set to 3 microseconds, you can see the 2 peaks, and that's your the TROSY and the anti-TROSY on the carbon dimension. But as you increase that delay to 8 milliseconds or 12 milliseconds, you can see the other peak completely vanish, and you get to see only the TROSY peak. So we have a natural selection over here for anything that's nothing bigger than 20 kilodaltons. You don't need to worry about the anti-TROSY line. So this pulse sequence now we are using is a simple head core. You go from proton to carbon, you encode the chemical shift of proton on the way, you do a simple refocusing, and then you detect on carbon. So here I show you the proton carbon correlation for HCA at both 25 degrees and 5 degrees. The spectra look beautiful. And one of the key advantages of this type of encoding is that you don't need an F19 probe. So you leverage the F19 TROSY effect without ever pulsing on F19. So you can run this on any of your standard triple resonance probe. Now, the question comes to is, which is better? That's, I think, it's more of a philosophical question at this particular point. Here I show you 2 different spectra. Here is the proton-carbon correlation, especially choosing the TROSY with respect to the fluorine. And here's a simple carbon-fluorine TROSY that we have shown before. Now, if you look at the carbon line width in both cases, one is the proton carbon as well as the carbon fluorine, they're pretty much the same. So even at 5 degrees, the line width on average is about 6 hertz on carbon. Now, if you look at the line width on the fluorine, on the proton or the fluorine side, now you can see that the proton line widths are extremely narrow. They're isotropic, the CSA is isotropic, and they're extremely narrow. Whereas the fluorine line widths are about 10 times that of the proton line width. Yet, the proton resonances are narrowed, are spread in about a ppm, whereas the fluorine resonances are spread about in 10 ppm. So what is resolution here? In terms of line width, proton is better, but in terms of seeing the peaks, I think both of them are same, which also tells you one of the advantages of using a fluorine NMR in addressing these biological systems. Now, the other thing that we were cognizant of is what are the structural perturbations that will happen when we introduce a fluorinated amino acid into the protein. And that's actually one of the reasons we chose human carbonic anhydrase. And here I show you the overlay of the 4-fluorophenylalanine label sample with the wild type. This is an N15 HSQC. And you'll see there's a lot of changes over here. And we were initially alarmed by these changes. But we're also aware of the fact that the fluorine causes ring crunch, causes a change in electronic environment, even though the structural changes need not be big. So we went ahead and solved the crystal structures of both the 4-fluorophenylalanine as well as the 3-fluorotyrosine labeled HCA, and compared them with the wild type human carbonic anhydrase. To our surprise, the structures were near identical. What we initially thought would be more of a perturbating substitution, which is the 3-fluorotyrosine, was actually the best. So it had an RMSD with a wild type of about 0.06. And the 4-fluoroalanine was a little bit worse, but still very close. Now, previously I also mentioned this concept of ring flips. So especially with the 3-fluorotyrosine, the system is no longer symmetric. We observed this initially in our TROSY experiment. And here, these are these minor populations. And at that time, we attributed it to ring flip, but we did not have any concrete evidence for it. But now we have the structure of these proteins solved to a very high resolution. And actually, we can see these ring flips. So essentially, what we can see is that we can see density for both forms of the tyrosine. And we can actually use this information in a refinement. So you can see that there are two conformers, one in blue and the other in, these are taken from the crystal structures, one in blue, the other in orange. And for some of the residues, for example, residue 40 or residue, in this case, I think it should be residue 193, residue 40 and residue 127, it's existing in only a single conformation, whereas something like residue 193 exists in two conformations, and you can see the two conformations in the structure over here. The resolution of the crystal structure here is about 1.1 angstroms, and actually you can see the density for fluorine in one conformation as well as in two different conformations. Whereas the 4-fluorophenylalanine is always in a single conformation. Now, this effect, the TROSY effect, is not only enjoyed by amino acids, especially the aromatic amino acids, it is also enjoyed by the nucleobases. And here we show theoretical calculations using spinach for different substitutions of fluorine on nucleobases. And especially something like fluoroadenine, you can see that it has a very low, very slow relaxation rate when it's fluorinated. And especially people trying to use this for nucleic acid or also as an ATP that's bound to a protein would see some remarkable effects over here. So at that time, when we published it, we didn't have a way to make C13 label fluorinated nucleobases. So what we did was we made a DNA with fluorinated uracil in this case, and we used the natural abundance C13 to show the TROSY effect. And here you can show that this is a coupled spectra, and you can clearly see the TROSY effect on the top of the TROSY component on the carbon. And here we show you the selection of the TROSY and the anti-TROSY effect. And this was recently followed up by some very nice work from the group of Christoph Kreutz at Innsbruck, where they have successfully made a couple of versions of C13 F19 labeled nucleobases, and using a synthesizer, they were able to incorporate them into RNA and show the TROSY effect in RNA. And I think there's a recent study I was just told that is coming from the lab of Kwaku, who has used this in combination with runoff transcription, where you can also incorporate these bases using a runoff transcription system. So with that, I hope in conclusion, I've shown you that the F19 C13 TROSY provides an opportunity to probe structure and dynamics of large systems. The dynamics is a part that I didn't go into in much detail. There's work by Scott Prosser and others that's shown that we can probably approach the low micromolar, the low microsecond timescale. We are working on some methods to assign these fluorinated amino acids, both using dipolar as well as scalar coupling. The TROSY effect does not depend much on deuteration, so it could also be used in systems that are where deuteration is impermissible. The heteronuclear NOE, especially between proton and fluorine, could provide unambiguous constraints, especially leveraging the chemical dispersion in fluorine. And we're also working on RDZ measurements, because if we look at the carbon dimension, there are two peaks that are pretty strong, so we can use this to measure RDCs. And one of the things that comes to my mind is that, can we feed rabbits with C13F19 labeled phenylalanine and get some antibodies and look at them? So with that, I would like to thank the people who actually did the work. The NMR, the sample preparation was done by Andras, Abhinav, and Sandeep. And Akshay for running some of the controls that we're doing using mass spec to see how much of incorporation is getting done. Paul for developing optimal control pulses, which we are going to use in some of the toxi transfers that I haven't talked about. And Ilya for all the help at Spinach, and Gerhard and co for being a part and parcel of this particular this project. For all the synthesis of the amino acid, we couldn't have done it without Vlado and Danny at the University of Sofia. And a huge thanks to Bruker. In fact, we do not have a probe that can record fluorine over here. So all the experiments that I showed you was recorded in the Bruker facility with help from people like Wolfgang Bermel, Helena Kovacs, and Clemens. With that, I would like to conclude, and I'll be more than happy to take any questions.
Thank you, Hari. So again, if you have questions, type them into the Q&A. And I'll convey them to Hari, or raise your hand if you want to ask a question verbally, and we'll unmute you. While questions start, let me ask a first question. I don't like to think about the synthetic problems, but if you had two fluorines, would there be a substantial CSA-CSA TROSY effect?
We haven't thought about that. So essentially, the idea is to put two fluorines in adjacent positions on the ring.
Right, and then the zero quantum spectrum one might think would have a CSA-CSA TROSY, which Pravushin had also looked at years ago.
We haven't thought about that particular problem, but I think Brian Sykes has looked at the methyl TROSY, if it would exist in CF3, and that doesn't exist. But we haven't thought about the CSA, CSE on the ring.
Okay, well, that answers one of the questions that's already come in. What can you do with the CF3 group?
Yes, the CF3 group is, meaning I think Brian Sykes has looked at the CF3 group and there isn't, but I'm not sure if a CFH2 or CF2H or CF2D could be a system that should be looked at. And the first question is how to make it is one of the questions. That's something which I don't know, but CF3 is not there. There's a JBNMR article by Brian Sykes that has looked at that.
So Walter Chazen asks, with your 4-fluoro-Phe, why are you using the 3-bond carbon-13 proton coupling rather than a 2-bond coupling to the meta position?
Two reasons. One is that it's easy to deuterate that one, and the coupling I think is pretty similar, if I'm not mistaken. I think the coupling is about the meta and the ortho coupling are pretty similar. That's my understanding of it, and it's easy to deuterate the position that is meta to the fluorine, that's ortho to the fluorine, so that you get a slower relaxation on the proton side.
And Fred Damberger asks, are the populations of the two ring flip conformations correlated between the X-ray structure and the NMR data that you have?
Nope. One was frozen, the other one wasn't. We haven't, no, the answer is no. We are looking into this to see if we can gain anything from that, and we don't know what we would learn from that, but yes, the answer is no. And we are also a little bit hampered in the process because we don't have all the assignments for the MVP, but maybe it'll, for the HCA in this case, maybe it'll light up something once we get that.
So I think a follow-up to what you had talked about, what other amino acids, fluoroserine, trifluoroalanine, any of these applicable?
These would not have the TROSY effect. And so we haven't looked into what would happen with that. Because here
And
the Trojan
again,
effect is enjoyed by the carbon, and the CSE of the carbon is what gets reduced over here. And that's what we are observing here.
but again, there's still perhaps the question of CF2H or
Yes.
CHF2, spin systems.
And also CFD2 or all those combinations needs to be tried. So probably we need a friend who is a chemist who can make all those molecules.
And Ilya Kuprov points out in answer to my question that there should be a CSA cross-correlation effect, and then probably also a 19F long-lived singlet state. So more work to do.
I think probably people like Angela and other people would scream if we put two fluorines on the same ring. The biology would probably be compromised.
And a question about applications in solid state NMR.
Oh, that May
speak
and
for Angela and May.
Yes, Angela, May, and Tatiana have done some phenomenal work on that, and I think you should hear it from them.
And have you, so a question as to whether you've measured the time scale of the ring flips.
We haven't. We have not measured the time scale of the ring flip in this one. Again, we are waiting for some additional time. If Clemens is on the line, he could, the sample is right there. We have the experiments, we just need the time.
And let's see, I think in interest of time, we'll leave the other questions for the informal talk afterwards, and you'll also be able, I think, to see them in the Q&A and answer them yourself.
Yes.
And with that, I'll let me thank Hari again and turn things over to May to introduce our next speaker.
Okay, thank you. All right. It's a pleasure to introduce our second speaker today, Paul Schanda. All right, so Paul studied chemistry at the University of Vienna in Austria. There he already did undergraduate research in using solution NMR to study protein dynamics in Robert Conrad's lab. And so after having grown up in the Austrian Alps, he then moved to the French Alps and did his PhD work in physics at the University of Grenoble in the lab of Bernhard Bucher. And there he developed the so-called SOFAST HMQC method to speed up the measurement of 2D and 3D solution NMR spectra. After that, he went back east to the Swiss Alps and did postdoctoral research in Bert Meyer's lab at ETH, where he made the transition to solid-state NMR and developed Eudor-based methods to quantify the amplitudes of molecular motion. In 2010, he started his own group at the Institute of Structural Biology at Grenoble, where he has launched a fairly successful and very multifaceted program to investigate the structure and dynamics of large enzyme complexes, mitochondria membrane protein transporters, as well as chaperones that shepherd these transporters to the right membrane. And these studies are carried out in a very interdisciplinary manner, integrating solution NMR, solid state NMR, cryo-EM, SACS, MD simulations, etc. And in addition, he has continued to spearhead development of solid-state NMR techniques for studying dynamics, particularly R1 row relaxation dispersion experiments under magic angle spinning. So, today he's going to tell us about large protein complexes as studied by an integrated structural biology approaches. Paul, welcome.
Yes. Thanks a lot, May, for the kind introduction. And thanks for the organizers for putting up this very nice webinar series. Are you seeing my screen? I believe so. So as you said, May, I'm going to look at large protein assemblies in today's talk using primarily solid-state NMR, but also cryo-EM and MD simulations. And I'd like to start by thanking the people who actually did most of the work. And I had a great postdoc in my lab, Diego Gauto, who did a lot of what you're seeing today. together with Adrien Favier, our platform engineer, and Alicia Vallée, and the initial samples came from Jérôme Boisbouvier. And I'd like to show you today in this presentation how we can determine a structure of a pretty large protein complex, half a megadalton approximately, using NMR data and cryo-EM data, which individually are insufficient to actually determine a structure. But by combined, we can actually determine the structure. And then I'll look into the dynamics of these functional motions as well as some motions of aromatics. This somehow echoes the previous talk. And I'd very briefly introduce a tool that we are developing to make solid-state NMR much more efficient and much faster in terms of acquisition. So I don't need to say much about this slide here. We are interested in complexes of tens to hundreds of kilodaltons, and you all know that it is challenging to do so. In solution, we have slow tumbling, rapid T2, and this is of course reflected also in the statistics. If you look into the protein database and you look up the protein structures that have been determined using NMR spectroscopy, then you see that NMR is doing pretty well up to, let's say, 20 kilodalton, but then it rapidly drops, and there are hardly any proteins above, let's say, 40 kilodaltons of which a structure has been solved. And the protein that we are going to look at today is this particular protein here, which is called TET2, which is about 500 kilodalton, and it's an aminopeptidase, so it's an enzyme formed of 12 copies of 39 kilodalton subunits. So in any case, we are well beyond the usual range where NMR spectroscopy would determine structures. So is it actually worth it, or should we just do cryo-EM? Because cryo-EM is really very strong nowadays. And indeed, we got a pretty nice cryo-EM data set. These are our collaborators at IBS, and they determined a 4.1 angstrom or so resolution cryo-EM map. And we actually thought that we would solve the structure with this, but we actually failed because 4.1 angstrom is not quite enough, at least in our hands, to actually determine a structure. And if you consider that the average resolution for maps, EM maps deposited these days on the EM database are even higher than that, it's clear that atomic resolution in cryo-EM is not really yet the rule. And of course, cryo-EM does not directly provide information about dynamics, so that's good news. NMR is still somehow in business. And so we primarily do magic angle spinning solid-state NMR spectroscopy, and even though this is a very large protein, we can actually get very nice spectra. So here you see different flavors, so either a deuterated sample where we would look at HN, proton-detected spectra. This is the somewhat old school, but still very successful carbon-detected kind of approach. If you specifically label, then you can get very nice probes of either methyls or aromatics. So in this case, we don't use fluorine, but we use CH labels of aromatic rings. And if you spin fast enough, let's say 100 kilohertz or so, you actually don't need very fancy labeling, and you get pretty decent spectra, proton-detected spectra of this large protein. So with this kind of spectra, we actually managed to assign this. This is not necessarily trivial because it's 350 something residues. So we combined a couple of 3D and 4D experiments to do so. And Astrid did a great job assigning this, but it took her many, many months. And afterwards, we figured out that actually Flyer can do the job basically overnight. So it's a great program here. And this is the kind of extent of assignment that we get. So all the black residues are assigned, only the blue ones are missing. And you can see that this correlates somehow with B factors. Other people have seen this. So the more flexible, the less chance we have to assign it, because our dipolar transfers don't work that well anymore. Particularly interesting is this loop here, which is invisible in the crystal structure, and we also have a hard time seeing it. We only see a couple of signals there. So once we have this assignment, we immediately get, of course, the secondary structure using Talos. And so we are on the way to the structure, but of course what we need are distance restraints. And so this is the experiment that provided most of the distance restraints. It is a solid-state, three-dimensional experiment that has two simultaneous nitrogen and carbon dimensions here, and a proton dimension linking two protons together. So you get transfer between methyl protons as well as from a methyl to a backbone and from backbone to backbone and H's. If you label your molecule properly, again, this echoes a little bit the talk that we just had. In this case, we use C13 proton labels and all the rest is deuterated. Then you additionally get contacts between phenylalanines and methyls or backbones. So putting this all together, plus about 20% of constraints coming additionally from solution state NMR NOESY spectra, we come up with about 500 distance restraints on top of the Talos restraints, which for a 350 residue protein is not a whole lot. And not surprisingly, the structure calculation using a pretty standard Siena structure calculation approach basically failed to converge. Nevertheless, you can actually see that secondary structures are reasonably well defined and their arrangement is kind of okayish in the different structures, but we clearly lack long distance information. So maybe we should go back to cryo-EM. And of course, we are not the first ones who think of combining cryo-EM with NMR spectroscopy, but arguably this is a pretty complicated system because the monomer size is really large. And as I already mentioned before, the cryo-EM map by itself did not allow us to solve the structure de novo. However, what you can very easily see are alpha helices. So you can see this even in a map that is truncated to 8 angstrom resolution. There are tools out there that even allow you to get this in a fully automatic way. So we know in 3D space where we have this kind of sausage things that are helices. And we know in sequence space where along sequence we have secondary structure elements. This comes from Talos. So basically, the way we try to combine this is to somehow fit those elements along sequence into these sausages in 3D space, which is not a trivial problem because we don't know obviously who is where. So it's kind of an assignment problem. Which helix goes into which structural element, into which electron density in 3D space. And so this is where Adrien and Diego came up with this very clever and elegant algorithm. And basically what they do is kind of an NMR style structure calculation. So they use NMR restraints. And in addition, they extract a few restraints from the EM map. And the restraints that they extract are basically distances between one residue in the middle of a given helix and all the other central residues of the other 5 helices. We used only the 5 longest helices because they're easy to detect. So for example, we would put residue 341 into the center of this helix here. We would put 277 into the center of this yellow helix, 191 into the center of this green helix, and so on. And this gives you immediately very powerful long-range restraints. Only a couple of them, but they are really powerful. But obviously, we don't know whether we had the right solution, whether our assignment was correct. So we have to do this in a combinatorial way. We have to go through all the possibilities and then come up with some way of identifying the right solution. And so the way we identify the right solution is by looking at some kind of score that reflects the agreement of the structure with the NMR restraints. So this is simply the Siena target score, and some kind of score that tells you how well the structure fits into the electron density of these helices that we chose. So here you see 2 examples, this one here, which is actually a good one, and this one, which is a rather bad one. So the good one has actually 5 correct assignments of helix in sequence to sausage in 3D space. And you can see that although we restrained only the central residue, the helices line up pretty well inside the electron density. Whereas in this case, the structure is pretty constrained and actually the helices don't want to fit into the electron density. And so it turns out that the best scoring structure is actually the correct helix sausage assignment. So after this is done, we have kind of an initial fold, and you're seeing here the crystal structure of the monomer and our first structure. You can see, of course, that many things are wrong still, but kind of the overall fold is there. So what we need to do is we have to go and somehow refine this. And we do this iteratively by using the initial structure that came from this Siena run, flexibly fit it with tools that electron microscopy people like to use, such that the secondary structures fit a little bit better into electron density. From there on, you can define new restraints of atoms within electron density. You can come up with new unambiguous NMR restraints, and you cycle this a couple of times, and you see the bundle RMSD going down until you decide that you want to refine this thing. And in the final step of refinement, we use explore NH and explicitly use the electron density plus the NMR data. And this is the final result. So with this 4.1 angstrom EM map, we actually get a structure that is about 1 angstrom RMSD, backbone RMSD to the crystal structure. And I think more importantly even, it would have also worked, or it actually works, we tried it by truncating the map to a lower resolution. So in an 8 angstrom map, where you really don't have any chance to my knowledge at least, to get any structure from the EM map only, you still get a reasonably well-defined fold for this molecule. So let me tell you a little bit about the function of this aminopeptidase. So it cleaves peptides up to 20 residues in length from the N-terminus on a millisecond timescale. It forms a large cavity, and we have seen many similar examples, for example, from Louis Kay's group, also in protein quality control machineries. So substrates would enter this cavity, and then they would be cleaved at these catalytic sites, which are highlighted here in green. Interestingly, when you look into the X-ray structure, then there is a part missing here. This is the electron density from the X-ray structure. And this part is a loop region. And if you take this loop region, if you model it, or if you take it from our combined EM NMR structure, it turns out that it fills up almost 1/3 of this cavity. So out of curiosity, we said, well, maybe it's important, this loop, because it sits in the catalytic chamber. So we went on and mutated this. So we basically chopped off this whole loop here and connected residue 119 to 139 to have a very short loop. And the NMR spectra are almost identical. The structure is fine, but the activity is almost gone. So a loop that is not even visible in crystal structure is actually apparently quite important for the function. So this sounds like we have to look into dynamics here to understand what's going on. And I'd like to say a few words about how we can actually probe dynamics by NMR, or in particular in solids. So this is a simulation from Nikolai Skrinikov's group on ubiquity in crystals. And you can see that although it's called a solid, there is actually a lot of motion going on. And if you actually zoom into a pretty famous part of ubiquity, and this is a beta turn, then you can actually see that there is also some longer range motion. So here you just have seen a peptide flipping. And this comes with, all this motion comes with fluctuations of interactions. So that's what we can see by NMR. So the interactions that fluctuate are isotropic chemical shifts, as you have just seen with this peptide flipping, as well as dipolar couplings and CSAs. So how can we probe this? Well, if it occurs on the right time scale, then this isotropic chemical shift fluctuation can be seen by Bloch-McConnell relaxation dispersion experiments, T2 or T1 row type. And these are very famous in solution and very powerful. And on top of this, you also get, of course, relaxation, also in liquids, of course, but in liquids, relaxation is mostly dominated by overall tumbling. But in solids, the fluctuation of dipolar couplings and CSAs gives rise to relaxation. And as I'll show you in a minute, a thing called relaxation dispersion near the rotary resonance. And it furthermore gives rise to a reduction of the dipolar coupling, so we can actually measure dipolar order parameters directly in the solid. So let me say a few words about these relaxation dispersion experiments. Here is the equation for R1 rho in the solid. So it's a spin lock experiment. You would typically do this in N15 or C13, and you spin lock the nucleus with some RF field, which has an amplitude omega-1. And in contrast to solution state, here we have an additional term in the spectral density, and that is the spectral, the frequency of magic angle spinning. So what is important for R1 rho relaxation in solids are sums and differences of RF field and MAS frequency. And so this is in the order of several kilohertz typically. So if you have motion of the order of several kilohertz, then this should really become a dominant term for R1 rho. And you can actually see this here. This is R1 rho as a function of the time scale of motion. This is simulated. And you can see that if the motion occurs on a time scale of a few thousand per second, then you get this strong dependence of R1 rho as a function of the RF field, keeping MAS frequency fixed, or as a function of MAS frequency, keeping the RF field fixed. You can plot this differently, varying now the spin lock RF amplitude, and you see these relaxation dispersions, which strongly increases as the RF field approaches the rotary resonance condition. And for some reason, we call this NRD, near rotary resonance relaxation dispersion. Of course, this exists on top of the usual Bloch-McConnell relaxation dispersion. So here again is data for ubiquitin for this peptide bond flip here, where you see this has been studied extensively in solution state NMR by a couple of groups, where you see here the Bloch-McConnell part, and here you see this NRD part. And both of them provide complementary information because the NRD part actually tells you about the geometrical, the amplitude of motion. You see these effects not only at the n=1 rotary resonance condition, but also as the half rotary resonance condition. So when the RF field is half the MAS frequency. This is particularly seen for protons, for example, not so much for nitrogens. So let me go back to this loop that we were interested in TET. As I said, the peaks of this loop are pretty weak. So we do have one particularly nice probe, which is a valine methyl group, CHD2 methyl group, which sits right here in this loop, just before these two prolines and this histidine. And so we can use this probe to actually learn something about the loop motion. And the first thing that we can do to understand the dynamics is to measure the dipolar coupling, the hydrogen-carbon dipolar coupling, using a reader experiment. And so here are the kind of raw data. And you can readily see that valine 120 clearly has by far the lowest order parameter, which reflects the fact that this loop is highly dynamic with an order parameter below 0.2. We can go on and measure carbon-13 R1 rho relaxation dispersion experiments, NRD experiments, and you can see that for almost all residues, except this guy here, you get flat or almost flat NRD relaxation dispersion profiles, showing that these residues do not undergo microsecond dynamics, while you get a very strong effect here for valine 120. And we can actually fit this, and the time scale of this motion is something in the 10 microsecond time scale. So far, so good. So we know that the loop is moving, but where actually is it? We can learn about this indirectly because we can look at the protein, the wild type protein, and the loop deleted variant of it. And the idea is that if part of this molecule here, so here I'm showing just a dimer from the inside, if some residue here is in transient contact with the loop, then chopping off the loop would change the average chemical environment, and therefore the chemical shift would be somewhat different. And all these red residues indeed have a different chemical shift in this loop deleted variant compared to the wild type. And you see that it goes all the way from the entry pore to the active site. So basically more or less the whole cavity inside is in transient contact with the loop. This is also reflected by MD simulations done by Alessandro Barducci. That also shows basically the same kind of coverage of contact. And interestingly, also co-evolution of residues with the loop show the same kind of pattern. So, but what is it actually doing, this loop? If you look into the sequence, you find that there is a histidine, a highly conserved histidine, as well as two prolines. And in some remotely homologous protein, there is actually, this histidine is actually visible. And it points towards the active site of the neighboring monomer. And we speculated that this histidine may actually stabilize somehow the substrate in the active site and thereby have a role in the catalytic turnover. So if this was true, then we should actually get an effect by mutating this histidine or the prolines just adjacent to it, which are also highly conserved. And these are activity data where you see that the Km Michaelis-Menten constant increases, not dramatically by a factor of 4 or 5, let's say, but still this supports the idea that this enzyme substrate complex is actually destabilized in these mutants. So the picture that we have is that this loop samples many different conformations. And if you add a substrate or also an inhibitor, then this histidine would actually transiently interact with the substrate, and thereby it would shift the equilibrium towards the right here. We can go and probe this by using a substrate analog, an inhibitor, which is stably bound. And indeed, if you add this inhibitor to the wild-type protein, you see this peak of valine 120 undergoing a pretty well-defined shift here. It also gets weaker, so maybe the time scale is changing. And if you do the same experiment with a mutant which has a phenylalanine instead of this histidine, then the peak corresponding to valine 120 just next to this histidine position is hardly changed upon adding the inhibitor, which supports the idea that if you don't have a histidine here but a phenylalanine, you still have the same kind of conformational ensemble here, whether you have substrate or not. So this is our idea here. Substrates would enter this large cavity. They would encounter a forest of loops until they reach the active site, where the loop or the histidine in this loop would be able to transiently stabilize this complex, thereby facilitating the enzymatic turnover. As this really echoes Hari's talk, I'd like to say a few words about phenylalanine labeling. So now we are not so much interested in function, but more in the methods or in more fundamental aspects. So we came up, or not we, but actually Kainescho's group or Lichtenecker's group, they have two different ways of labeling phenylalanines with a single hydrogen-carbon pair in an otherwise completely deuterated system, or two hydrogen-carbon pairs in the ortho position in an otherwise completely deuterated and C12 system. So in TET, there are 10 phenylalanines, so you would expect 10 peaks, and indeed, you get about 10 residues here for the parasite, which we assigned by mutagenesis and some RFDR data. So far, so good. But for the ortho site, where you would expect also at least 10, maybe even 20 if there is no ring flips, residues or peaks, you actually only see, let's say, 4. So maybe there is some interesting dynamics going on. So we went on and measured dipolar couplings for the parasites, and you can see here reader data again. And basically the order parameters for the para are very high, meaning that the axis of the ring is not moving. However, those phenylalanine ortho sites that we see, those 4 that we see, have a very low order parameter, and we can very well describe them with ring flips. So this is a model which explicitly takes into account ring flips, and it fits pretty perfectly our data. So this means that all the phenylalanines that we actually see must be on the fast time scale. They must be flipping, and they must be flipping on the fast time scale. So we can go on and measure R1 row. As I've shown before, this has this particular curve. It's RF dependent on the slow branch, but it's independent of RF on the fast branch. And this allows you to actually know whether you are on the left or on the right here. And this allowed us to say that the ring flips occur on a time scale of tens of nanoseconds. So why don't we see the others? Well, we also did MD simulations, and it turns out that those phenylalanines that we actually see, so there's 26, 84, 176, and 232, are actually rapidly flipping in the MD simulation, while the others are not, meaning that they are stuck in one minimum, so they are probably exchanging on a slow time scale, slow enough to increase the T2 relaxation to a level where we don't see those anymore. If this is true, then we should actually be able to freeze them out by going to low temperature. So basically, from a regime where we have very fast transverse relaxation, would slow them down to see them again. And this is exactly what we see. So this is room temperature, and we go down to 100 Kelvin, and we see a bunch of peaks. We didn't assign them, but clearly we have a lot of peaks. Interestingly, they are pretty sharp, so that's also interesting at 100 Kelvin. And we can also go and actually measure the thermal activation of ring flips by measuring temperature dependence of relaxation parameters. So there is this interesting inflection here at about 200, 220 Kelvin. I don't want to speculate about this, but it's kind of interesting because it coincides with glass transition temperatures that many other people have reported on. In the very last few slides, I'd like to say a few words about a tool that we are developing to make solid-state NMR data acquisition much faster and much easier, I believe. So assume that you want to collect this experiment here, a 4-dimensional proton-detected experiment. Well, what you have to do is you have to optimize a bunch of things. You have to optimize all the CP steps, all the pulses, selective pulses, decoupling, and so on. And this is usually tedious, it's time-consuming, and it may be error-prone. So can we make something that is a bit more straightforward? And actually, we developed this tool here, which has multiple optimization tools. So to calibrate all the transfer steps, all the pulses that you need. It also works in a more logical way. It works in kilohertz basis and not in dB or watts. And of course, you also want to make sure that you have a reasonable pulse sequence. So we have also compiled a sequence library that contains currently more than 100 sequences for resonance assignment, for collecting distance restraints, for measuring dynamics. So basically all the experiments that I've shown today are in this library. And it contains a bunch of additional tools. And of course, it also contains the possibility to add your favorite pulse sequence in a very straightforward manner with a couple of clicks. So it's basically the work of Alicia, and it's built upon the solution state variant of AnimalLib, which has been developed by Adrien and Bernhard, which is very successful and very useful. So the idea is that you have on a common mounting point, which can be one of the spectrometers or an external computer, you have all your Python scripts for setup and all your pulse sequences. So all the spectrometers would access this central library, and you would launch AnimalLib from within Topspin. So if you do so, you see a menu where you can choose all your experiments. So let's go a little bit through some of them. So here we would like to use a proton-detected calibration experiment to calibrate, for example, the proton pulse via a HN experiment. If you click this button, then it opens a window that lets you choose a couple of parameters, but only the ones that you're really interested in. So for example, what kind of ramp do you have and so on. And it would directly start the calibration. It would save the calibrated value into some table, and it would know it forever. So whenever you go and want to start a more complicated experiment, let's say this one here, it would actually, again, do all this routing. It would load the pulse sequence and so on. It would load all the relevant parameters and all the calibration that you have already determined, and open this window, which summarizes all the parameters that you still may want to look at. And the idea is that if you click the accept button, you have an experiment that works. And this is actually really the case, almost always. It's quite amazing. And so the idea is that instead of having to deal with all these parameters, which you forget from one time to the next, AnimalLib proposes you just the important parameters, and it even comes up with a reasonable guess or propositions for the parameters that you want to use. So with this, I'd like to stop, and I'd like to thank all the people. So as I said already, Diego has been the motor of this TED project. Has been a very nice collaboration also with group of Jerome and the cryo-EM people. I mentioned Alessandro Barducci. I mentioned this outstanding program from Peter Güntert's lab. Charles Schwieters has been very helpful with setting up ExploreNH. And please feel free to get in touch with us about the solid state animal library. We are very happy to share it. And with this, I'm happy to take questions.
Thank you, Paul, for an excellent talk. I would like to start with my first question. I find it intriguing that your 353 residue protein that you said in the end could have been assigned by this flyer program. Can you tell us a little bit about the kind of line width you get on this protein? What is the condition under which that this is automated assignment could actually be possible?
Yeah. So actually, this was already a couple of years ago, and when I started, I didn't have a proton detection probe, a fast spinning probe. So most of it was actually done with carbon detection.
Okay.
So we did. So this is the list of experiments that we used, and we did actually almost all of it on a 600. So you don't really need very high field for this, at least in this case. The 4D experiments turned out to be really crucial. Because in a 2D experiment like an NCA, you hardly have the resolution to get individual peaks. So the idea here is that you have a kind of a root spectrum, which is not a 2D but a 3D, and then you would extend it to each side by 1 or 2 spins. And these 4Ds turn out to be really crucial. So if you remove from this flyer run the 4Ds, even one of them, the whole thing breaks down. So you really need them. What we also did for the manual assignment, I may have it, no, I don't, is selective labeling. So we had a couple of, indeed I don't have it, sorry. We had a couple of samples with selective labeling of amino acid types, 2 or 3 amino acid types, and then you get very useful starting points. So these starting points turned out to be really crucial for the manual assignment because you have so many options. But if you remove those selectively labeled samples from the flyer run, it actually works just as with those spectra. So flyer is apparently, it tries sufficient combinations to actually be able to assign it without any selective labeling.
Okay, all right. So let me get to the Q&As. So Konstantin Maniv asks, is there some, well, hold on, so that's the CF3, sorry. Let me go to Lusky's question. How are the different subunits of the protein different from each other in your TET2 complex?
They are symmetric. So they're all the same. And of course, that's crucial because that means that we have one set of peaks.
Yeah.
And not 12.
And you can tell, the resolution is good enough for you to tell that there is only one set.
Absolutely, yeah.
Anonymous attendee, for the histidine to phenylalanine mutation, does the inhibitor still bind? Did you complete the KDs? Oh, did you compare the KDs?
So we did NMR experiments, chemical shift mapping, and basically we see the same picture. So it still binds to the same site, and it's strongly bound. We didn't do any KD measurements, but it's a high affinity binding.
Okay. So Lucille Friedman asks a great talk, thanks. Question regarding the NERD phenomenon. Is it a relaxation effect of the kind that you described with red field theory, or is it an interference between 2 coherent effects, meaning spin lock and MAS, to which you contribute some spectral line shapes, or convolute spectral line shapes?
Okay. It comes straight out of the red field theory. So it is really a relaxation phenomenon. So these are the equations, and if you plug in these equations, then you get this kind of phenomenon. So it really is just a relaxation effect. What is maybe interesting or not completely understood, at least by me, is what happens when you really hit the resonance condition. So obviously at some point you start recoupling things. So we actually usually save some space here so we don't go quite to the rotary resonance condition. And we don't really know where we stop. Usually we stop, let's say, 3 kilohertz below.
Okay. So Fred Daumberger asks, can you relate the rate limiting step, oops, just jumps, for the enzyme to the conformational dynamics timescale of the histidine containing loop?
Yeah, we would have dreamed that this would happen, but so the timescale of the loop motion is about 10 microseconds. And the timescale of the enzyme is somewhere in the 4 milliseconds or so. So I would not dare, you know, it would be nice.
Yeah. Okay. David Calburn asks, with regard to the phenylalanine ring flips, the MD simulations seem to show some significant variation of rates in the NMR detected resonances. Can the spectra or enhancements provide more specific timescales for the flips? Great talk and very interesting integration of EM and NMR.
Thank you. So yeah, it's true that this guy here flipped only a couple of times while these here flip all the time. But so I don't have a table here, but it's somewhere in the paper. Actually, they are all somewhere in the range of 5 to 15 nanoseconds. So we don't see a big difference. Which, well, I mean, NMR could be wrong, but it's also not completely excluded that the force fields are not quite accurate enough to actually get the transition states properly sampled. And so maybe the timescales are not quite right from the MD.
Okay. There's another question about, is the loop motion a consequence of protein cis-trans isomerization? And do you have assignments for the protein 121 and protein 122 ring carbons to decipher if they're in trans or cis conformations?
It's also an excellent question, and I would love to have the answer, but I don't. So we really don't see the backbone. I mean, we see a few residues, but then it very rapidly drops the signal, and we don't see these prolines.
Mm-hmm.
But it would be great.
So Tom Schmidt asks, methyl groups come to a close to complete freeze at around 40 to 50 Kelvin with slight variations. However, other relaxation factors will kick in, Hobbs effect. So for the phenylalanine, you mentioned that they will come to a complete stop at around 100 Kelvin. Does relaxation effect, are relaxation effects still present, and any idea what they're like, what they are, like ring flip-flopping, so that there's something here. Yeah.
Yeah, that would be very interesting. And Clinton Emsley's group and Martin Blackledge and Joseph Lewandowski have looked into this pretty carefully. We didn't. We just had 2 weeks or so on that machine to collect these data. So I don't know a whole lot about what is still there in terms of residual motion. There is, so that the signals are appearing already at, let's say, 220, 200. So I don't know if there is really a sharp transition here. In terms of relaxation, there seems to be a sharp transition, but of course, relaxation is highly sensitive to the time scale. So just because in terms of relaxation, there's not much change anymore, it doesn't mean that there is not change anymore in terms of dynamics.
Mm-hmm.
Yeah, so to make it short, I don't really know.
Mm-hmm. There are more questions. So Rasmus Linzer asks, said a very nice talk. How did you actually determine what maximum power or spin lock duration you could safely go for in the carbon nerd experiment?
So we did a couple of nitrogen nerds at 45 kilohertz MAS. And so that was fine. We went up to 42 or so for 50 milliseconds. But yeah, so this worked. And so that carbon was not a problem anymore at that point, because I knew that carbon could go higher. But the first one was, well, I discussed with people from Bruker at some point. They didn't really want to say much because obviously they cannot guarantee. So I just tried and it worked out at 40 something kilohertz for nitrogen.
Okay.
But it was a bit scary.
So Sankaran asks, would it be possible to label with paramagnetic nitroxide side-directed labeling and use DEER to get additional long-range distance information?
Yeah, so all these FRET, DEER, PREs, everything is very welcome to basically, I think, and I hope that we can come up with something where we don't need EM anymore.
Mm-hmm.
I mean, not that I have anything against it, but it would be pretty elegant to only use NMR.
Yeah. Or Lusky asks, you showed a loop deleted spectrum. What kind of mutant was that and what was the replacement?
Okay, so the loop deleted spectrum is a spectrum of a sample in which we chopped off residues 120 to 138 or so. Let me just show this here. So basically we just had a mutant where we removed all these red residues. So it goes from this residue directly into this one.
Okay.
So the loop is just shorter.
All right. Last question about your solid state NMR lib. The library tool in TopSpin sounds like a useful method for solid state NMR folks. How is this integrated in the software? And have you already talked to Booker about incorporating this into future TopSpin versions?
Well, obviously there are a lot of commercial aspects. Then if you integrate this into a commercial software or into Bruker software, for the moment it's free for academics. So the liquid state version of it has been downloaded more than 100 times and it's apparently used by many labs, so that's very useful. It is integrated in the sense that you start it directly from within TopSpin and it actually uses Python scripts which act within TopSpin. So I would say it's pretty much integrated already. It's quite straightforward to install. So that the solid state version is not yet online, but we have beta testers that are fairly happy with it. So we are happy to provide it also. the solution state version is definitely something that you want to get if you do solution state NMR, I would say, because
Okay.
it's so easy.
Yeah, Paul, ready to get a lot of emails requesting for your library. So last question by Himanshu Singh. Great talk. Did you assign the histidine sidechain and looked at its tautomeric state? Could you also comment on its pKa?
No, we don't see this histidine sidechain. And we have this specific labeling of phenylalanines that I showed then later on. And actually, we also labeled the histidine to phenylalanine mutant. And I was hoping that I would see an 11th peak, you know, this additional phenylalanine coming up, and it did not. So I believe that this microsecond timescale motion also kills the sidechain signal for this particular phenylalanine, and only the methyl, which has this fast rotation, actually survives.
Mm-hmm. Okay. Good. I think in the interest of time, we're really half an hour after the hour. We will turn into an informal session. Thank you everyone for attending and also to the two speakers for a fantastic talk.